All right, this is part 2 of the limits at infinity series here. I'm going to have 3 parts, I think. These questions are a little different than the ones in part 1 in that you still have these large ratios and limits at infinity, but now we're bringing in some other kinds of powers on x. We've got some rational powers here. We've got some square roots in there, which are rational powers, right? And then this third one, you can see a sine function in the mix there as well. In the last one, we did have a couple exponential pieces in there to make it not just rational functions. But at this point, if you want to take a look and try to answer these yourself first, you could pause. I'm going to dive right in here in a second. And if we look at that first one, you can think of this a lot, very much the same way that you look at the rational functions. It's technically not rational, this function, because you have these non-integer powers on x, right? X to the 1/2, x to the 3/2. So it's not technically, it's not a polynomial over a polynomial, so it's not a rational function. And yet, the same kind of rules really work here. If you look at this first term on top, 5x radical x, you could write that as 5x to the 3/2 power. And the second one is 7x or negative 7x to the 1/2 power. And what happens is the x to the 3/2 power, being that it has a greater power, is going to, as x approaches infinity, is going to take over. And the minus 7x to the 1/2 becomes, again, piddly and insignificant by comparison. So that 5x to the 3/2 will take over on top. Kind of ignore that one. On the bottom, same idea. The x to the 3/2 power is the greater power because the other one is just 2x to the 1 power. And 1 is not as big as 3/2. So this one becomes piddly and insignificant by comparison. And so what we're really looking at is 5 times this really large number, right? X to the 3/2 as x gets really big, right? Divided by, get a different color here, divided by 1 times the exact same really large number, right? So it's 5 times a really large number divided by 1 times the same really large number. And then, yeah, you do have this other stuff here, right, that we are disregarding. It's still there, but by comparison, it's much smaller, so it doesn't matter as much. So what that means is 5 times a big number divided by 1 times the same big number is approximately, it's going to be 5, right? The whole thing without the limit, just this whole expression isn't actually equaling 5, right? Because you have these other small things on the top and bottom that change it a little bit, but those other things are insignificant by comparison, so we're really close to 5. So what you look at, and that's what the limit is then, the limit actually equals 5. Okay, again, so what you look at when you have multiple terms on the top and bottom that are power function terms, in other words, some constant times x to some constant power, then you can look at the greatest degree. X to the 3/2 wins on top, and x to the 3/2 wins on the bottom. This other stuff doesn't, and so our answer is just 5. Okay? There's another trick I'm going to show you in a minute after the next problem that we could apply here if you wanted to maybe be a little more convincing with your work and kind of prove it. But that kind of smell test where you just look at the highest degree, it does work there. All right, I'm going to erase some of the extra junk there too so we can look at it again in a minute. This does equal 5. All right, on this next one, if you give that kind of a similar look, you might be thinking, hey, on top we have x squared, and on the bottom we kind of have x squared, right? If I just triggered a thought there, I'd say pause and think about it for a minute. I'm going to keep going though. So yeah, that's pretty much true. We have x squared on top, and we basically have x squared on the bottom. The problem is this minus 7. And I guess the question is, how much does that minus 7 matter? How much does it affect the value? And if it was on the outside of a square root on the bottom, we would say, oh, we could probably ignore that because as x gets really large, minus 7 becomes, again, piddly and insignificant, I like to say. Inside the square root, it's actually even more piddly and insignificant. Let me show you what I mean. If you looked at, say, 100 squared, right? 100 squared is 10,000. if you take the square root of 10,000, of course you get 100, right? If I subtract 7 from it first, you're almost at 100. It's not 7 less than 100. It's like 99 point, probably 9 something. I'm not even going to put it in a calculator right now. You can try it if you like, but it's very close to 100. So subtracting 7 under that radical actually does far less to change it than subtracting 7 on the outside of the radical would. So that 7 is, again, piddly and insignificant by comparison. And it is true that this limit is going to be the same if we just ignore the 7. And it ends up being 1, as you might guess. However, there's an algebraic trick I want to show you here that I think helps to really clear it up. And it's the same one we can use on that first one we did, and a lot of these to help clear it up, these limits at infinity. What we're going to do is we're going to multiply the top and bottom of this fraction by 1 over x squared. But on the bottom, 1 over x squared doesn't work as well with the square root. So what I'm going to do instead is multiply by the square root of 1 over x to the 4th. Right? So what I'm really doing here, I'm trying to do that multiply by 1 technique, right? We multiply by a creative version of 1. So something over itself, and that way we don't change the value. Well, first of all, am I actually multiplying by 1 here? Are those two things equal, that numerator and denominator? That's an important question. So let's double check that. 1 over x squared, does that equal the square root of 1 over x to the 4th? And it does. If you're dealing with real numbers, then the square root, well, first of all, the square root of a fraction is the square root of the numerator over the square root of the denominator, right? And the square root of x to the 4th, again, in the realm of real numbers, is x squared. Okay. Now you might have a flag going off, like a red flag, like, ooh, let's be careful here. And that's good if you do, because the square root of x squared is not just x. People want it to be, but if x is negative, then those are not equal. This will be positive and this can be negative. So again, we're talking about with real numbers here. So it's actually true that you need absolute values when you say the square root of x squared equals x. It's actually equal to the absolute value of x. You don't really need the absolute values on the x squared though, because x squared is going to be positive anyway, as long as x is a real number. And again, I keep saying real numbers. That's all we're only talking about real numbers here. So yes, it is true that these two things, this numerator and denominator, for our purposes are equal to each other. So we're going to go ahead and use that. And what this does, let me get rid of this really quick. What this does for us is it lets us kind of simplify the inside of this limit in a way, I don't know if simplify is the right word, but manipulate it in a way that it makes it a lot easier to see what the limit is through direct substitution. When I distribute 1 over x squared on top, I just get 1, right? X squared over x squared. On the bottom, because it's in a square root, I designed it that way, I can actually distribute right into the square root. I can distribute this 1 over x to the 4th in to both of these guys. And so what I get is 1, because it's x to the 4th over x to the 4th, minus 7 over x to the 4th. And now, through direct substitution, you can see that when you plug a very large negative number in for x here and take it to the 4th power, the bigger that value is, the more this is true, the closer this gets to 0. So we're actually approaching, through direct substitution, 1 over the square root of 1 minus 0. And I left off the limit now because I was able to get a clear answer through direct substitution. So I don't need the limit anymore. I've done that. And so I actually get 1 as an answer, just like we said at the beginning. It is in fact equal to 1. Okay, again, that's a really good trick. You can do the same trick up here. I won't go through it all, but if you multiply the top and bottom of this by 1 over, let's just say x to the 3/2 power, and you'll have the same thing happen. Here, they'll cancel out. You'll just get 5. Here, you'll get 7 over x. As x gets really big, that goes to 0. Here, you'll get 2 over a square root of x, 2 over x to the 1/2. That'll approach 0. And here, you'll just get 1. And so you'll have 5 over 1, which is 5, same answer. Okay, last one on this page, this one with the sine in it. And when you're looking at that, if you think of kind of the rules we've been looking at with the degrees, you're going to be looking at probably the 5/2 degrees here, right? Or the power, 5/2 power. That's bigger than the second power. But there's also this sine function with a 5th power inside of it. Come back to that. On the bottom, it's just a straight up polynomial, and it's 3rd degree. Okay. So then the question is, does this x to the 5th in here matter on top? And pause it if you want to think about it for a minute. But I will tell you now, that does not matter. That x to the 5th does not matter. It does not matter what function of x is in here, as long as we don't have any like domain issues, which we don't, right? This is a 5th degree polynomial. It's the domain is all real numbers. You can plug anything in you want for x. The sine of whatever that is, a sine function is bounded by -1 to 1, right? If I multiply it by 5 and include that, now we're looking at -5 to 5. So this whole thing now boxed in green is at most 5 and at least -5. And what are we doing with it? We're just adding it in the numerator. It's piddly and insignificant as x gets large, right? Especially this term. This term is going to take over on top when x approaches positive infinity, and that's going to be that. Just a quick side note, if I had x going to negative infinity, I'd have a domain problem here because that 5/2 has a square root in it and a negative inside the square root. Again, we're dealing with real numbers. But positive infinity, no such problem. And so on top, the only thing that's going to really matter for the limit is the 2x to the 5/2 power. On the bottom, it's going to be the 4x to the 3rd power. 3 is greater than 5/2, so this entire thing approaches 0. You can just do it like that. If you want to multiply both the top and bottom by 1 over x cubed, what will happen is on top, every single term will have a kind of a leftover x to a power on the bottom, right? And as x goes to infinity, those will all go to 0. In the denominator, that will happen with the last 2 terms, but not with the first one. You'll just get 4. And so you'll have 0 over 4, which is 0. And that's it. That's going to do it for part 2 of this little short series on evaluating limits at infinity. I'm going to do one more problem one more set of problems that involve some more square roots that are a little funky. We're going to use that same trick we just talked about in part 3.